Welcome to the class on stability criteria for discrete time systems. Today we will discuss two different stability criteria for discrete time systems. The first is the jury criterion. However, before we discuss this criterion in detail, let's consider what impact the position of the poles has on the stability of the system. For a stable discrete time system, all its poles must be inside the unit circle. However, if any pole is outside the unit circle, the discrete time system is unstable. If a system has no poles outside the unit circle, and at the same time has single poles on the unit circle, the system is marginally stable, and it can have any number of such poles. It is important that they all are single. However, if any pole on the unit circle is more than 1/4, then such a system is already unstable, even if it has no poles outside the unit circle. It is necessary to know these dependencies because based on the position of the poles, we will determine what system we are dealing with: stable, unstable, or marginally stable. The jury criterion uses the Marden table, which must be completed first. The slide shows the beginning of such a table. The first column contains the names of subsequent polynomials. This column must be filled correctly. The fourth column contains the parameters of subsequent polynomials. We complete the first row with the parameters of the characteristic polynomial, starting with the parameter at the lowest power. The second line should be rewritten, but in reverse order. This is so-called adjunct polynomial and is denoted by an asterisk. Adjunct polynomials have reciprocal roots. Let's take a very simple example. A characteristic polynomial z plus 2. So the pole is in -2, and the root also is at -2. The adjunct polynomial of z plus 2 is 2z plus 1. The root of the polynomial 2z plus 1 is -1/2, which is the reciprocal of -2. The third column contains delta values. They are very important because on their basis we will draw conclusions about the stability of the system. The second column, containing the row number, can be omitted. We simply rewrite the first two rows of Marden table based on the denominator of the transfer function, but the subsequent rows need to be calculated. These values are determinants, where the two left elements of the determinant are the same every time, and they are these two elements. Whereas we take the remaining two elements of the determinant starting from the right side. For the first parameter, there will be these two elements. For the second parameter, there will be these two elements, and so on. And we always use the last two rows for calculations. As a result of the calculations, each subsequent pair of rows has one parameter less. We repeat calculations until there is one element left in the fourth column, and this should be for delta m, where m is the system order. Once we have the table completed, we look at the delta values and specifically at their signs. In the next step, we need to determine the signs of the products pi. Each such product is the result of multiplying all deltas from the first to the ith. Any product less than 0 means a pole inside the unit circle, and any product greater than 0 means a pole outside the unit circle. We don't know where exactly these poles are located, but to assess the stability of a system, we only need to know whether they are inside or outside the unit circle. Two special cases may occur during calculations: a zeroth row or a 0 in the first column. And since I am the one who arranges the content of the tasks, they will almost certainly happen. If you get a zeroth row, take the last normal row and write it as a polynomial. Let me remind you that from the left there is an intercept, and subsequent parameters occur with increasingly higher power of z. One needs to calculate the derivative of the variable z from this polynomial, and finally calculate the adjunct polynomial. The polynomial obtained in this way should be included in the next Marden table, but care should be taken to ensure the correct numbering. One has to change the letter of the polynomial because it is already a different polynomial. I will just add that this asterisk in these problems means an adjunct polynomial, but please do not associate it in any way with the Laplacian star transformation, which appeared in discrete block diagrams. Unfortunately, the marking is the same, but it means something completely different. Moreover, after a zeroth row appearance, conclusions should be drawn in a slightly different way. I recommend marking it with a vertical line between the products pi, between which it occurred. Products before a zeroth row mean the same as before. If there were several zeroth rows, we consider each group between the zeroth rows separately. In each such group, we combine positive and negative products. Each such pair represents one pole inside the unit circle and one pole outside the unit circle. However, the unpaired products represent the poles on the unit circle. Moreover, poles located on the unit circle in subsequent groups indicate poles located in the same places as the previous ones. That is, their multiplicity increases. Therefore, in the example presented, we should draw the conclusion that we have 3 poles inside the unit circle and 4 poles on the unit circle. But of these 4 poles on the unit circle, we have 1 two-fold pole and 2 one-fold poles. Therefore, the system is unstable. And I would like to point out that if the system is unstable, even if there are no poles outside the unit circle, then you must also write in the answer that it is caused by multiple poles on the unit circle. Now let's move on to the second special case. It is 0 in the first column, but any of the elements in the row must be non-zero. And here I'm warning you that the method of operation I'm describing is different than in the script and different than in some of my older materials. It is very possible that the professor during the lecture will require this method from the script, but I'm introducing this one because the one in the script requires remembering many more actions, doesn't always allow for obtaining the result, and I have also found cases where it distorts the obtained results. So what should you do when such a special case occurs? One needs to add one pole and repeat the calculations. We add the pole to the characteristic polynomial by multiplying it by z minus the pole. However, it cannot be either +1 or -1, because then we will not solve the problem. In most other cases, this will help. It doesn't matter what value we choose, and whether it will be a plus or minus. What is important is that at the very end, when writing the conclusions, we omit the pole added at this stage. Unfortunately, this was only the first of 2 criteria. Fortunately, the latter is partly a reminder of what, I hope, has already been. We will use the modified Routh criterion. I warn you that the content of the task will include the criterion that you will have to use. In the modified Routh criterion, one must first use the so-called Mobius transformation. In this way, the polynomial m of w is obtained. In the next step, it is best to get rid of denominators, that is, multiply the entire expression by the highest power of denominator. Once we obtain the characteristic polynomial, we carry out subsequent calculations in the same way as in the plain Routh criterion. Special cases may also occur in this criterion. We solve them in the same way as in the plain Routh criterion. Also, in the same way, we draw conclusions after the occurrence of zeroth row about the marginally stable poles. When writing your answer, please remember to refer to the unit circle, not the imaginary axis. But there may be one more special case in the modified Routh criterion. Typically, we will receive a polynomial that will have the same degree as the order of the system, and we will obtain information about exactly this number of poles. However, it may happen that the polynomial dependent on the variable w will be of lower degree than it should be. If this happens, then each degree too little means one pole at point 1, that is, on the unit circle. If something like this happens, you should normally perform the calculations for the reduced degree polynomial and add these poles on the unit circle in your conclusions. And then there is the modified Hurwitz criterion. Also in this case, one needs to use the Mobius transformation and obtain a polynomial depending on the variable w. Subsequent calculations are performed as in the Hurwitz criterion. However, I will not require this criterion during classes, and I only show it as a supplement. Quite a lot of theory, but it will probably be easier to understand with specific examples, so let's solve a few tasks. The content of the task is: using jury criterion, verify the stability of a system with a characteristic polynomial . We start from building a Marden table. We start filling with the parameter at the lowest power. At the power of -2, we have a parameter equal to 0. We complete the second line with numbers in the reverse order. The first is the determinant of -1/2, 2, 2, and -1/2. Now the determinant of -1/2, 2, 1, and 0. The last determinant of -1/2, 2, 0, and 1. We rewrite in reverse order. Delta 1 is equal to We perform subsequent calculations in the same way as before, By the way, I warn you, calculators will be useful during the tests, especially for this task. We don't have to enter a specific value. Information about the delta sign is enough. Please pay attention to the subscripts in the names of polynomials and deltas. These subscripts should be the same in the same line. Now let's write the signs of the subsequent products. Of course, we don't write these products. I wrote them to remind you. A product less than 0 indicates a pole inside the unit circle. This means that all poles are in the unit circle, so the system is stable. But in conclusions, I want not only information about the system, whether it is stable, unstable, or marginally stable, but also information about the poles' location and how many of them there are. We will use the jury criterion again, but this time we will verify the stability of a system with transfer function . The characteristic polynomial is denominator of the transfer function, so we use it to complete the Marden table. We enter the parameters starting from the one with the lowest power. We are dealing with a zeros row, so we need to calculate a new polynomial for the second delta. Let it be the polynomial n2 of z. According to the formula, one should take the last polynomial before the zeros row and calculate its derivative with respect to z. I forgot delta 1. Regardless of whether the task contained positive or negative powers, auxiliary polynomials during the task should always be taken with positive powers. Otherwise, we may not get the correct result. The parameters from the left are from the lowest power, that is, from 0 power. And finally, we need to calculate adjunct polynomial. Well, we need to create a new table, this time for n polynomials. Please pay attention to the correct numbering of polynomials and deltas. We are only interested in the signs of subsequent deltas, so the value in the last line does not need to be calculated, just mark whether it is greater than or less than 0. However, this field cannot be left blank. There was a zeros row, so it should be remembered when calculating products, and it is best to mark it with a vertical line. A negative delta before the zeros row denotes one pole inside the unit circle. After the zeros row, we need to combine the products in pairs, positive products with negative ones, no matter which one with which one. Each such pair represents one pole inside and one pole outside the unit circle, and poles without a pair are poles on the unit circle. So finally the system is unstable. and also pole's position. If anyone is curious, the initial transfer function can be written as The next task is to verify the stability of a system with a characteristic polynomial using the Routh criterion. And here is a digression. This is denominator of transfer function. Can we multiply denominator and numerator of the transfer function by something? Of course we can. Therefore, at this stage, we can both scale the parameters and change the powers, positive to negative or negative to positive, simply by multiplying times z to the appropriate power. However, you should be careful with the naming of polynomials. Subscripts must correspond to deltas, and two different polynomials cannot be named the same. So I will denote the next polynomial by n of z. We have a zeros row, and since the letter n is already taken, we take another one, for example, O. In the last line we received the value 0, which means we have a zeroth row. However, in this case, regardless of what value will be obtained as a result of the calculations, it will be the only value after a zeroth row, and therefore it will definitely not enter into any pair, and this last pole will be the pole on the unit circle. Therefore, as an exception, if a 0 appears in the last row, it can be left 0 and the product P equal to 0. Let's also mark where the zeroth rows were. The first product points to a pole inside the unit circle. Subsequent products cannot be paired, so the remaining 3 poles are on the unit circle. But I have already mentioned that the products after successive rows of zeros increase the multiplicity of the previous poles. In this case, the multiplicity of the pole on the unit circle. Therefore, we finally conclude that the system is unstable. If the system is unstable and the pole's position doesn't indicate this, then the conclusion should explain why this is so. The next task is to verify the stability of a system with a characteristic polynomial. We see that this time we are dealing with the second special case, that is 0 in the first column. And now please focus, because I am saying a very important thing. You can find a different description in both the script and all my older materials. The old solution is more difficult and sometimes doesn't return a result. However, the method I will show is analogous to Routh criterion, and I hope it will not cause any major problems. Take the initial polynomial with positive powers and add some pole by multiplying this polynomial times the appropriate binomial. The pole can be almost any. It can be stable or unstable, but unfortunately it cannot be on the unit circle, so the simplest option, z plus 1, is out. But z plus or minus 2 or a half, it can be. However, please see what would happen if we used z minus 2 in this case. At the highest power we would have a value of 2, and at the lowest, minus 2. And we should already see that if the first and last digits are the same, then 0 will appear again in the first column. But half will be fine. However, I don't like fractions, so I will take minus 3. And now we have to do all the calculations from the beginning for this new polynomial. Only at the end we have to discard the one unstable pole that we just added. Unfortunately, there is a danger that we choose such a value that 0 appears in the first column again. Then we simply go back and try to multiply the original polynomial times the other pole. We must always remember about the appropriate naming of polynomials. What I will show doesn't make much sense, because we are already at the very end of calculations, but I want to show you all the possibilities. The polynomial n3 of z looks like this. We can scale this polynomial without affecting the obtained conclusions. But, of course, you cannot change the sign, because these conclusions depend on it. So I can create another polynomial that will be 75 times smaller than n3 of z. It doesn't matter from which polynomial we take delta 3, only its sign is important. We discard one of the unstable poles because we added it, and we write the answer based on the remaining ones. Let's now move on to tasks related to the modified Routh criterion. We will verify the stability of a system which characteristic polynomial is First, we need to use the Mobius transformation. That is, we need to substitute This polynomial already depends on the variable w. Now we need to get rid of the fraction bar, so we multiply by w minus 1 to the power of 2. This is where the most common mistake occurs. This polynomial can no longer be named m of w, because such a polynomial was a line higher and had a different value. That's why this one here must be named in different way, no matter how, but in different way. Please pay attention during these calculations. You can easily make a lot of different mistakes at this stage and lose all the points for the task. Once we have this polynomial, we just need to build a root table and fill it. I assume that the root criterion has already been introduced, so everyone should know how to fill out this table. On the left you can mark where the poles are. Nothing can be said based on the first row. There is no sign change in the second row, so the pole is stable. I draw it on the left. There is a sign change in the last row, so the pole is unstable. I draw it on the right. Therefore, the system is unstable. Please remember to write conclusions in relation to the unit circle. We will again use the modified root criterion. Of course, similarly to the jury criterion, we can modify this characteristic polynomial at the beginning, as if we were multiplying numerator and denominator of the transfer function. We modified the polynomial, so we called it a little different. Now it's a different polynomial again, so we have to rename it again, either to a different letter or change the subscript. The ability to use abbreviated multiplication formulas is very useful in these tasks, as you have probably already noticed from what I wrote. It's also good to know how to use Pascal's triangle, which I will write now. In our case, this one before last row will be useful. And I will divide by 2 to get slightly smaller numbers, but in the root criterion they do not increase that much. We have a row of zeros, so we proceed as in the root criterion. There was no sign change anywhere, but one have to remember that there was a row of zeros. So we have 2 poles inside the unit circle and 2 poles on the unit circle. Another example for the modified root criterion. If we have negative powers in a characteristic polynomial, there is no need to convert them to positive ones. A negative power simply reverses the fraction. We are dealing here with a special case, 0 in the first column. In the case of the root criterion, I always recommend adding the pole at -1 because the calculations are the simplest. We just need to remember to ignore that one stable pole that we added. And the last task of stability verifying type. Let's take system whose characteristic polynomial is And please pay attention here to what is happening. Two highest powers have zeroed out. This is the last possible special case. Let me remind you that each zeroed power, counting from the highest one, is a pole on the unit circle, exactly at the point z equal to 1. But if the highest power doesn't reset to 0, nothing happens. This was the case in the previous task. As you can see, in this case, the root table is not particularly necessary, because without calculating you can see a specific value w, which will be the root of the polynomial, but I wrote it as a matter of principle. No sign change, so one pole is in the unit circle. Now we will move on to another type of task. So far we have analyzed where the poles of the system were located, but now our task will be to determine the range of parameter values for which the system will be stable. Let's consider a system with transfer function Our task is to find the range of gain values for which the system will be stable. Additionally, the content of the task may, but doesn't have to, include an additional condition for the range of gain values. Let's assume it must be greater than 0. The characteristic polynomial is the denominator of the transfer function. A quite common mistake is to leave a minus sign before the bracket. The sign must be in brackets, otherwise we will get incorrect result. Let's try to find the answer using Dewey criterion. Well, you can see that despite the relatively simple task, we are now entering such calculations that we cannot calculate it manually. So I will use a little help here. I also have it written on a piece of paper, so I will copy that result. Let's calculate the roots of this polynomial. What conditions must be met for the system to be stable? All products pi must be less than 0. So what values must deltas have? The first must be negative and the rest must be positive. This is what it looks like in general, and in this particular task, the parameter with the highest power is positive, so we start drawing the graph from the top. And this polynomial has to be less than 0, so for the second condition, c greater than 0, we have already calculated the roots. The parameter at the highest power is negative, so we start drawing from the bottom. The root 15/4 is double, so the graph bounces. And this polynomial was supposed to be greater than 0. So, what will be the final gain range that ensures all conditions are met? Please do not forget about the condition from the task content. Now let's try to solve the same problem using the modified Routh criterion. In the initial phase, we solve the task in the same way as before. And now that we have completed the root table, what conditions must be met for the system to be stable? There cannot be a sign change in the first column. That is, all three table elements must be greater than 0. But this was only the first set of conditions, because no sign change can also be the case when all of these elements are less than 0. This also needs to be considered. In this case, there is no gain that would meet these conditions. And the full range is the sum of both sets, when the first column is greater than 0 and when it is less than 0. So the final result is the range is from 0 because there was also a condition from the task content. And that's all I wanted to show you today. Thank you for your attention and have a nice day.